Hello, AP students. We will be looking at Chapter 17 today in your textbook. So we'll begin diving into material. This video will mostly focus on spontaneous processes and entropy, so 17.1 and 17.2 in the textbook. So what we want to think about here, all right, um, a lot's going to happen in Chapter 17, and we are going to refer to it every now and then as the alphabet soup chapter, all right, because we're going to see a lot of symbols. There are going to be a lot of our formulas. We should already feel comfortable with H, right? That is enthalpy, and we know that when delta H is negative, that is an exothermic reaction. It releases heat. And when delta H is positive, that's an endothermic reaction, a reaction that takes in heat. So we're going to be seeing a lot of deltas. We're going to see delta H, delta S, and delta G. All right, so we will sometimes refer to it as alphabet soup. All right, so just to clarify, um, this is thermodynamics. This is not kinetics, what we studied in chapter 12. So thermodynamics versus kinetics. So in our chart here, the domain of kinetics is the reaction pathway. All right, that's the activation energy. That's something that we can change with the catalyst. That's something that we look at in reaction mechanisms. All right, but kinetics, it's the rate of a reaction. It depends on the pathway from reactants to products. So kinetics is how fast a reaction takes place. Thermodynamics has nothing to do with speed, but thermodynamics does tell us whether a reaction is spontaneous based only on the properties of reactants and products. Right? So when we looked at these energy diagrams, we know a reaction is exothermic or endothermic based on where the reactants and the products end. All right, there is more to that story that we'll be looking at this unit, but we are not looking at how fast the reaction occurs. All right, that would be kinetics, and we've already learned that. So the first thing I want to talk about is a spontaneous process. All right. You may have used the word spontaneous a number of times in your life, but what it means in regards to chemistry may be a little different. All right. So we think of something as spontaneous, a group of people just get together and they start dancing, they start singing, it's spontaneous. Well, we're only looking at the individual atoms and molecules now. All right. But I want to just think about some really common spontaneous process that we should know. A ball rolling down a hill. All right, if you put a ball on a hill, it will roll down. All right, that's a spontaneous process. And what does it mean? Spontaneous means it will occur without outside intervention. All right, if you want the ball to not roll down the hill, you have to have some kind of outside intervention, but that ball will roll down the hill without any. All right, gases, when they are opened up, they will spontaneously diffuse. All right, we saw that in chapter 5. If we had two containers with two different gases and we had a stopcock between them, once we opened it, they will begin to diffuse. That is a spontaneous process. It occurs without outside intervention. All right, and something like a snowball melting. All right, we actually had a senator bring one in to a meeting in Congress, right? It was a cold day in February. He brought in the snowball just to prove that global warming was not true. All right, I'm not going to comment on that, but as part of his demonstration, while he was going about his presentation, the snowball melted. All right, that snowball melted on its own there in that room. All right, it occurred without outside intervention, so we can say that was a spontaneous process. All right, now thinking about snow though, I just want to think spontaneous, no outside intervention. When it's really cold outside and it rains, we will get icicles that form spontaneously. Now, if it's really warm outside and you've made a snowman, that snowman will melt on its own spontaneously. So, what water will do kind of depends on its surroundings. So, if it's really cold, it'll spontaneously freeze, and if it's really warm, it'll spontaneously melt. All right. Water above 100 degrees Celsius will spontaneously change from a liquid to a gas. So there is going to be a lot to this story. Our surroundings are going to matter, but we'll kind of, hold off on that for a second. So a spontaneous process occurs without any outside intervention. A spontaneous process may occur slowly over thousands of years or fast, right, in less than a second. We tend to think things like combustion, we like to think of as spontaneous, but because they occur fast, but that is not always the case. All right, some really slow process that are spontaneous: rusting. All right, my truck has been on this earth for more than 20 years now, and it has continued to rust to a point where I might have to be getting rid of it soon. All right, but it didn't happen quickly, but it's happening without any outside intervention. All right, the amount of heat given off or absorbed is not what determines how fast the reaction takes place. However, exothermic reactions do tend to be spontaneous, all right? But an endothermic reaction can be spontaneous as well. So that's not the full story, whether it's endo or exothermic. So entropy. This is something that we have certainly um, observed in the classroom several times over. You talk to any teacher, anytime the class tends to go towards disorder, that's entropy. All right, entropy is a measure of disorder. So our two pictures here, we have all the Legos spread out all over the place. Lots of disorder, that is a lot of entropy. All right, when we throw a deck of cards, right, kids love to play 52 card pickup. That is a lot of entropy. So entropy, it's gonna get the symbol S. All right, so that's gonna be important. Anytime we see S, that represents our entropy. It is a measure of the randomness or disorder. All right, the driving force for a spontaneous process is an increase in the entropy of the universe. All right, something will be spontaneous if it makes the universe more random or has more disorder. All right, which is why I would argue we have a lot of spontaneous process happening in our AP classroom. All right, because we are always headed towards disorder. Now, entropy is a thermodynamic function. It describes the number of arrangements that are available to a system. So we'll look at a couple of pictures of the different arrangements, what that looks like at that molecular level. And nature proceeds towards the states that have the highest probabilities of existing. All right, nature tends towards disorder and randomness. So here we have 4 different molecules of a gas. All right, and we're shown 5 different states that they could be in and the different possible arrangements. So we see all the way on the left, right, we have all 4 molecules of gas together in the flask on the left. All the way on the right, we see all 4 molecules of gas together in the flask on the right. Those 2 outer examples can happen. There's nothing to say that it can't happen, but it's very unlikely that it will happen. All right, we're thinking about the probability of these states. So we could have 3 in one and 1 molecule of gas in the other. We see that in images 2 and 4. And again, it's possible. All right, it's a little more likely than all 4 in just one, but the highest probability we have is 2 molecules of gas in one container, 2 in the other. All right, now since they have different colors, they could be arranged in all different patterns. All right, so this gives us more possible states, which is why it is more probable that it is going to occur. Now, if we think about entropy with the state of matter, a solid has the least amount of entropy because it's the most organized. All right. As we move from solid to liquid, the particles are able to spread out and they are able to take on more states. So that's why the entropy of a liquid is higher than the entropy of a solid. And then as we keep spreading out, when we get into that gas phase, we get the most possible states. So that means that we have the most randomness, the most disorder. So a gas would have the most entropy if we're looking at solid, liquid, and gas. Now, even with the gas though, I just want to think back to Boyle's law, right? At a low pressure, we have a high volume, and at a high pressure, we have a low volume. The low volume that we see with that high pressure has less possible states, so it has less entropy than the gas at low pressure. So volume is a really important key to understanding entropy. The more volume a system has, the more volume whatever we're looking at has, the more possible states. So more volume is always going to mean more entropy. All right, so solids have the least volume relative to the liquid and the gas, so that's why they have the least entropy. All right, now entropy, we are going to be looking at delta S. We don't want to get this messed up. So delta S, again, it's S final minus S initial. So the final entropy state minus the initial entropy state. So when we have a positive delta S, right, final entropy is greater than initial entropy. So when we have a positive delta S, we had an increase in entropy. That means we had an increase in disorder. 52 card pickup, that would be a positive delta S, right? Because we have created the disorder. Now, a negative delta S means that the final entropy is less than the initial entropy. So a negative delta S means a decrease in entropy, all right? That means that we have moved towards having less disorder, right? Less randomness. So we organize something, we put something together. All right, so last night, me and my wife, we were working on building a Lego creation, right? We were organizing those pieces. There was a decrease in entropy, right? Our final product will have the least amount of disorder of all of the different states. All right, admittedly, I did just open the package and dump it everywhere. So we started with a lot of entropy, and then we worked our way towards having less. All right, now, just a little bit of practice. For each of the following pairs, choose the substance with the higher positional entropy. So if we had solid carbon dioxide and gaseous carbon dioxide, I want you to just pause for a second. Which one has more entropy? And of course, this one is easy. It's going to be the gaseous carbon dioxide, right? The gaseous carbon dioxide, there are more positions that those molecules can take, right? It's also going to have a larger volume. Now, our second example, N2 gas at 1 atmosphere of pressure and N2 gas at 1.0 times 10 to the negative second atmospheres of pressure. There's nothing here about the temperature, so we don't have to worry about anything like that. This would be strictly a Boyle's law. All right, since they're both a gas, we want the gas with the larger volume. Which gas would have the larger volume? The N2 at 1 times 10 to the negative second atmospheres. So that substance would have the higher positional entropy. It would have more disorder because it has more states that it can exist in. All right, now predicting entropy changes. Predict the sign of the entropy change, delta S, for each of the following processes. Solid sugar is added to water to form a solution. So our initial entropy is the solid sugar, all right? Packed close together, not that much disorder. Its final form is a solution where it has dissolved and all of those sugar molecules are spread out. They are taking up way more positions now. So the solid sugar being added to water to form a solution, that is going to have a positive delta S. There has been an increase in entropy. Again, an increase in the randomness. Those sugar molecules are all throughout the solution now. Iodine vapor condenses on a cold surface to form solid iodine. All right, it's condensing. We have a phase change, right? We're going from the gas state to a liquid. All right, so the volume is decreasing. We actually have less randomness now. We have actually created some order. So in this example, delta S is going to be negative, right? There is actually less entropy, less randomness by the end of the example. All right, so now the last thing I want to talk about is the laws of thermodynamics. All right, there's 3 important laws. They kind of govern all of these systems we look at. There are many different forms of these laws. So you will see, especially if you go on in the engineering field, you will see these things come up again and again, certainly in mechanical engineering. We have this zeroth law. It's kind of something we take for granted, but 2 bodies in thermal equilibrium are at the same temperature. All right, that's like when we would do our Q equals MC delta T problems, and we would drop the hot metal into the cold liquid, and they would reach thermal equilibrium, right? Heat always flows from hot to cold. We know that, right? We've seen the first law here. Energy can never be created or destroyed. So the energy in the universe, it's just changing forms. We know that delta E equals Q plus W, right? It equals our heat plus our work. But now we're looking at the second law of thermodynamics. The total entropy of the universe must increase in every spontaneous process. All right. Anytime a spontaneous process occurs, there is an increase in the entropy of the universe. All right. So we do not go backwards. The universe is only getting more and more disorder. That's where it's moving towards. We have more entropy in the universe. We have more disorder. All right. So the another way we can write it is that the delta S total is equal to the delta S of the system plus the delta S of the surroundings. All right. Now that delta S total will also write as delta S of the universe. All right. So entropy is not conserved. It is not something that, we move back and forth between the two forms. It is always moving towards disorder in the universe. So we can see something like a block of ice. As it melts, the delta S increases. Now, if we were to refreeze that water, the delta S would decrease. But only the spontaneous processes increase the delta S of the universe. So getting the water to go from the liquid back into the solid block may require a little more work, right? We would have to put it into something like a refrigerator. We would have to change its surroundings. So that would not be a spontaneous process, not in the example the way it's currently shown. All right. But if we were to take that block of ice at those surroundings, the entropy would increase when it melts. So again, for that second law of thermodynamics, in any spontaneous process, there's always an increase in the entropy of the universe. All right. Non-spontaneous processes do not have that, but the entropy of the universe is increasing, and for a given change to be spontaneous, the delta S of the universe must be positive. So that means the delta S of the system plus the delta S of the surroundings must be positive to make a process spontaneous. All right. If that is a negative value, then that means that it's just non-spontaneous. All right. Which might mean that we have to put an energy for that. All right. And if it were equal to 0, it would be a process that would be at an equilibrium where it would have no tendency to go either which way. All right. So again, entropy of the universe is always increasing, which is why entropy has been referred to as the arrow of time. All right. So I remember back when I was in high school reading an article about entropy, about it being the arrow of time. And I wish I could find that article. I found something close. So I will be providing that with this video, something that I'd like you to look at just to think about what entropy is. It'll be a huge piece as we move forward in this unit and learn more about what makes something spontaneous.